Chapter 11 deals with the properties of gases and the aspects of gases that relate them one to another. In the first section, we'll be looking at a little bit of background about gases versus pressure. We'll look at something known as the kinetic molecular theory, and we'll start talking about what is pressure when dealing with gases. So in the first section, the idea is brought up of kids in a restaurant attaching straws together, trying to make a really long straw to drink out of. And the author wants to know, how long is too long if you are trying to make a long straw for drinking soda? Is there any limit to the length of straw that you can make? Well, in order to answer that question, we need to know how a straw works in the first place. So what happens when you use a straw is not so much that you're drawing the liquid up through the straw as you are changing the pressure from the inside of the straw to the outside. So what's happening is when you drink from a straw, as you suck in, you're removing some of the air molecules from the inside of the straw, and you create a pressure difference. So what's happening is the pressure on the liquid in the glass that's outside of the straw is higher than the pressure on the liquid that's in the straw as you're drawing those molecules out. So the molecules of air, if you look in the picture here, you can see all these molecules of the air. Those are pressing down on the surface of your soda, and they're forcing the liquid up into the straw until it reaches your mouth. So again, this question is posed. If you had a perfect material to make a straw, where there were perfect seals between straws, or where there were no seals at all. If you had a solid straw with a good firm wall that's not going to collapse on you, how long can you make it? Well, even with the perfect straw, the longest straw you're going to be able to get is only about 34 feet long, about little less than 10.5 meters. So it doesn't matter how perfect your straw is, doesn't matter how good your lungs are, you're never going to be able to get liquid up higher than about 34 feet in a straw. Why is this? Well, it's because of that pressure that we're talking about. Pressure is the force being exerted per unit area by these gas molecules as they collide with the surfaces around them. Okay, and so, as these molecules are colliding, that's what causes pressure. It's just the collision of molecules and the transfer of energy in those molecules. So assuming you're at sea level, the gas molecules in the atmosphere around us are exerting a pressure of 101,325 newtons per square meter, or maybe a term you're more familiar with, about 14.7 pounds per square inch, or PSI. Okay, and there are lots of different pressure units, but here's a couple of them that we're talking about. That is also, and we'll see that in a minute, if you've ever heard of an atmosphere of pressure, that's 1 atmosphere is at sea level. So when you put a straw down in a glass of, let's say, orange soda, now just when you drop the straw in there, when it's open, as you see in the first figure here, the pressure inside and outside the straw are the same. There's no difference, so the liquid level should be the same on the inside and the outside of the straw. Now, when a person sucks on the straw, what they're doing is lowering the pressure inside the straw. So now the pressure on the surface of the liquid, is pushing down and then forcing that liquid up into the straw. Same idea if you've ever taken a straw and put your thumb over the end. You're not actually removing any molecules, but you're preventing the equalization of pressure. You're locking it into place so the pressure can't change. So when you lift that straw out of the liquid, all the liquid remains in the straw. It doesn't fall out because it can't change in terms of pressure. So why the 10.3 meters? Why the 34 feet? Well, if we get a perfect vacuum, okay, let's say we take a vacuum pump, so you're not trying to do this with your own lungs. You use a vacuum pump, and you pump all of the air molecules out of your really long straw. Well, then all we've got here is whatever pressure is being exerted downward by air molecules. And again, now this is assuming we're at approximately sea level, but it doesn't vary that much on the surface of the Earth. So the pressure of our atmosphere can only push a liquid up to about 10 meters, okay, maybe a little bit more than 10 meters. So a column of liquid, okay, 10.3 meters high, is going to exert the same pressure downward as gas molecules just open to the atmosphere. Okay, same amount of pressure there. So you're never going to get it to go higher than that without changing atmospheric pressure, without changing the force being exerted on the liquid that is on the outside of the straw. Okay, so the key to a straw is the pressure difference between the inside of the straw and the liquid that's outside of it. So we're dependent upon internal pressure in the straw and external pressure. Perfect vacuum, highest we're going to get it, is about 34 feet, 10.3 meters. Okay, here is that pressure that we have there, 1 atmosphere. So how do we put this into thought? How do we describe this? Well, what scientists use to describe this sort of relationship is and other relationships, other aspects of gases, is something known as the kinetic molecular theory. You might also see it abbreviated as the KMT. So if anyone's ever talking about the KMT, they're talking about the kinetic molecular theory of gases. And it's simply a model to understand how gases behave. It just helps to predict how, the correct behavior for a gas under a variety of conditions. Now, as we've seen with any other model, models are models. They're not perfect. They don't perfectly mimic something. They just help to describe it. And they will break down under certain conditions. But what we will focus on are the conditions where this model works well. And this is going to be for something known as an ideal gas. Okay, so we'll be talking about that in a minute. But what is the KMT? Okay, there are 4 aspects to the kinetic molecular theory. Okay, number 1 is that gases are a collection of particles which are in constant motion. There's constant movement in these particles. Even if they're really, really cold, even if they're in a solid, they're still moving. Okay, now we're not talking about solids, we're talking about gases. So keep in mind, everything in here is relevant to gases. All right, now in gases, there are no attractions or repulsions between particles. So they are not going to come together and stick. They are not going to force each other apart like a magnet. They're just going to move around and bounce off each other. So they do collide. When they do, just think of it like billiard balls. So like you're playing pool. What happens when a pool ball hits? Well, energy gets transferred and they bounce off in different directions. Same thing with particles in a gas. Premise number 3. In a gas, there's a lot of space between the particles relative to the size of the particle themselves. So in a gas, the particle size is essentially irrelevant because of the vast amount of space between them. They do come together and hit, but they're not crowded in any way. And number 4, the speed of the particles is going to increase with increasing temperature, which makes sense because an increase in temperature is indicative of an increase in energy. And the more energy you have transferred to these particles, the faster they're going to move. All right, so just rephrasing it a little bit different for gases. A gas is a collection of particles that move in constant straight line motion. Okay, so unless something gets in their way, the particles continue to move in a straight line. They do not attract or repel each other. They don't interact other than collisions and bouncing off each other. Okay, there's a lot of space between particles. And the energy of motion, the kinetic energy of the particles, is proportional to the temperature of the gas. Okay, now notice this phrase right here. It's proportional to the temperature of the gas in kelvins. So this means that, just as you increase the temperature, they have more energy. They're going to move faster. But notice the kelvins part. Okay, so if you remember way back at the beginning of the semester, we talked about the unit, the SI unit for temperature, and it is Kelvin. There's a reason for that. It's an absolute temperature, and we need that when we talk about gases. All right, so kinetic molecular theory helps us to explain certain properties of gases, such as the fact that gases are compressible. There's a lot of space between them, so if I do squeeze them down, if I apply pressure, there's space for them to come together. Okay, so I can compress a gas. If you've ever seen a gas cylinder, you know that we can do that. A gas, like a liquid, will assume the shape of its container. It also assumes the volume of the container. It fills the space that it's in. Okay, and gases have low densities when compared to liquids and solids. They're just, there's a lot of space in there. There isn't as much stuff. So very low densities. All right, so looking at some of these, the compressibility of gases. So if we look on the left, imagine you have a cylinder and you have a certain number of gas particles in there. Now you can count them if you want, I'm not going to, but there's the same number of particles in the container on the left as on the right. All right, and we put them in this cylinder and we put a piston on there. Okay, and we start applying pressure to the piston, we mash it down. What we see happens is, because of the empty space, we can compress them down. The particles get a little closer together. They're still movable. They're still going to move around, but they just don't have quite as much space to move. But we can squeeze those in. Okay, now, as compared to liquids, if we did the same thing with a liquid, we put it in the container and put a piston on there and then started applying pressure, we're not going to see a change in the volume. They're not compressible. So you might get a little bit of compression, but relatively speaking, there's so little space between the liquid particles, you're just not going to compress them. If you apply enough pressure, you'll get them to go from the liquid phase to the solid phase, but they're not going to get a whole lot closer together. All right, we said a gas assumes the shape of its container. Because the particles are not attracted to one another, they're bouncing around like pinballs in a pinball machine. Not a lot of interactions between the particles, so they just move around in whatever space is available to them. It's like a room full of preschoolers, if you've ever seen them, and they're just running around the room, bouncing off the walls. So they're going to expand to fill that volume. Gases have low density as compared to solids and liquids because of that empty space. So just to kind of drive that point home, looking at this example, if we took a 12-ounce can of soda, which is 350 milliliters of liquid, sorry, didn't mean to cross it out there, and we take that and convert it to steam. Okay, so here's our orange soda. We're going to take just the water out of that soda, and we're going to heat it up until it turns into steam. What volume is that steam going to occupy? That steam, as long as we don't apply pressure, as long as we don't pressurize it, we let it expand as much as it needs to, it's going to then, if we put it in a giant balloon and let it inflate itself, it's going to fill a volume of 595 liters. So we're going from 350 milliliters to 595 liters, the equivalent of 1,700 soda cans worth of volume. Okay, now again, that is to maintain the same pressure and temperature or whatnot. We're just letting it expand as much as it needs to in that case. The density of the steam at 1 atmosphere of pressure and 100 degrees Celsius would only be about 0.0006 grams per cubic centimeter or grams per milliliter. So you can see when we say low density, I mean extremely low density. And this is at atmospheric pressure and at the boiling point, just as the steam converts to gas. Pressure. So we want to define pressure. I think everyone knows the term pressure, and we have sort of an innate sense of what pressure is. But again, this is science. We want to define it scientifically. What actually on the molecular level is going on when we talk about pressure? Pressure is just what results from those collisions. So we said these things are colliding like billiard balls. As they collide, they are going to exert this pressure. They're going to exert an influence on their surroundings. And it's because of pressure that we can drink from straws, that we can inflate a balloon, that we can inflate basketballs and footballs. We can breathe. We can move air in and out of our lungs because of pressure. If we didn't have pressure, or we had too much pressure, that would really mess up our lungs. Anybody who's ever gone diving, if you dive without a tank, you know that the deeper underwater you go, the more pressure is being exerted on you, the harder it becomes to breathe. Well, not that you're breathing underwater, but it becomes harder to hold that air in. There's a pressure on there. It makes you want to release that air. Now, we also feel variations in pressure in the atmosphere itself. So variations in pressure create wind. So when you're feeling wind, you're feeling a change in pressure. If you have a barometer, if you've ever seen, they talk about when there's a storm front moving in, they talk about the barometric pressure rising or dropping. Okay, that's a change in the atmospheric pressure that indicates there's a high pressure front, low pressure front moving in. There's some sort of change occurring in the air. Okay, so pressure is important all around us. It's important to our bodies. We have internal pressure that has to be maintained, blood pressure. Okay, not quite the same as gas pressure, but it's pressure being exerted by the dissolved gases in our blood inside our body, okay, and the blood itself. Pressure in our ears. So if you have ever been out riding and you're riding around in the hills and you go up and down, you'll notice that your ears pop. If you go up in an airplane, if you climb a mountain, fewer molecules and the pressure starts dropping. And so what happens is the pressure inside your ear is higher than what's outside as it's dropping, and it creates, this sensation of pressure, pushing out on the inside of your ear, and it can be painful. So you feel this as pain until something happens to equilibrate that pressure. Okay, so once the air in your ears is the excess pressure, the excess air in your ear is allowed to escape, it equalizes the pressure and it doesn't hurt anymore. So this is why you're told to yawn, to chew gum, to try to do something to pop your jaw. What you're trying to do is move that opening, that seal, that membrane in your ear, try to get it open just enough to equalize the pressure so that you don't have that sensation of pain in your ear anymore. Now, pressure is a measurable quantity, so there's a mathematical formula for that. It is defined as the force per unit area. And if you've had physics, you know this one already. You've seen this one. It's just the amount of force being exerted by the particles over the area that the particles are expanding into. So it makes sense then, if pressure is what results from collisions between particles and the surfaces around the particles, that the more particles you have, the more pressure you would have, and the fewer particles, the lower pressure. So here we have the same volume in each case, and we're going to assume that other conditions are the same. The difference here is that the first container has fewer molecules. It would be a lower pressure. The more stuff we put in there, the higher the pressure gets. So it's kind of like inflating a balloon, except there we're allowing the volume to expand, but you know that it pushes out. The more particles you put in there, the more pressure it exerts, and the bigger your balloon gets. Now, I said a little bit earlier there are lots of units of pressure, and we want to look at some of those. What are the more common ones? Now, the simplest unit of pressure, and the one that you'll see probably the most often, is the atmosphere, and it's abbreviated as ATM, and that is just the average pressure at sea level. So again, if you're not at sea level, then you will have higher or lower atmospheres. If you're lower than sea level, you've got more atmosphere pushing on you. It will be a higher atmospheric pressure. The higher you go, the lower the atmospheric pressure. So, for instance, someone living in Denver, the mile-high city, is going to experience a significantly lower atmospheric pressure than somebody who's living in Death Valley, for instance, who's living at or below sea level. Now, there is the atmosphere, but that's not the one that is used in the metric system, the SI unit. Okay, the SI unit of pressure is the Pascal. And that is the one that we looked at a little bit earlier. It's defined as 1 Newton per square meter. Okay? And what is the relationship then? Now, again, the atmosphere is the one you'll see more often. The Pascal is the, quote, official unit. So it is helpful to know how to relate those two. Okay, pascals are much smaller than atmospheres. So it takes 101,325 pascals to equal 1 atmosphere. So even though the Pascal is the official unit, again, this is what you'll see more often. So atmospheres for human beings, you'll see generally right at, around or slightly less than 1 atmosphere. For example, in the area that we live, if you were to measure atmospheric pressure, you would find that it's usually anywhere between about 0.94 and 9.6 or 9.8, depending on the atmospheric pressure that day, if there's a storm front moving through or something. But it's not quite 1. If you have a really sensitive barometer, you can actually measure the difference in atmospheric pressure going from ground floor to, 3rd, 4th, 5th floor of a building. It's not much of a change. There's, a few pascals in there, but it's enough that if you have a sensitive barometer, you'll measure the difference. Now, another unit of pressure that you may be familiar with is that of millimeters of mercury. That's how it's abbreviated right there. And that originates from the original barometers. Barometers were made by measuring the height of a column of mercury. So the idea here, just like we had with our soda, if we had a container of soda, here we have a container of mercury. And we allow atmospheric pressure to push down on the surface of the mercury, and it forces mercury up into a column. Well, if you are at sea level, then the average atmospheric pressure at sea level is going to create a column that is 760 millimeters or 29.92 inches in height. So again, if you've ever looked at barometer readings, and you'll see, this number looks fairly familiar. They're usually right around this number, maybe a little lower. That's where that comes from. The reason we are using mercury, or we used to use mercury, to do that is because of its density. Mercury is the only liquid metal that we have. It's 13.5 times more dense than water. So remember, water, like the soda we talked about, if we had water or soda, we would need a column 34 feet high, okay, about 10 meters high, in order to be able to measure that influence of pressure. Well, if you have mercury, you only need about 30 inches. Okay, so only about 3 feet as opposed to 34 feet. So it's a huge difference there, and it makes it usable in that way. So that's why millimeters of mercury. Okay, you could do inches of mercury as well, but millimeters of mercury is what most people tend to report in scientifically. So what are the relationships between the units of pressure? Okay. Well, if I want to relate atmospheres, and you'll see everything gets related to atmospheres. 1 atmosphere is equal to 760 millimeters of mercury, just as we said earlier. There is another unit known as a torr, T-O-R-R. This is another very common unit that's used in laboratory measurements. And this was named after Italian physicist Evangelista Torricelli. This is the scientist who invented the barometer. So they were using mercury. So 1 millimeter of mercury is equivalent to 1 torr. Every millimeter of that mercury is a torr. So if you look at this, then 1 atmosphere is 760 millimeters of mercury. 1 millimeter of mercury is 1 torr. So this is also equal to 760 torr. I'm going to add that in because that's another one you'll see a lot, atmosphere to torr. So it's that same conversion factor. We mentioned PSI, so here's the equivalence for atmosphere to PSI, and then if you want to use inches of mercury instead of millimeters of mercury, if you have an old-fashioned barometer, then there's your relationship right there. Table 11.1 in your book gives a very nice summary of the more common units of pressure, so you may want to take a look at that one. You don't need to memorize all of these, but definitely know what an atmosphere is and know these two, millimeter of mercury and torr. Know that 1 atmosphere is 760 millimeters of mercury or 760 torr. Those are the ones that in a laboratory setting, again, that you'll see most often. This table also will be handy when you're working on homework. So again, don't try to memorize the table, but do know that atmosphere to torr or millimeter mercury relationship. Depending on the industry that you work in, the PSI may be more valuable as well. And what you'll tend to find is that wherever you're working, there's a preferred pressure unit. If you're dealing with pressure, you get to know that unit, you get to know the translation for that unit, so you'll get comfortable working in one particular unit. What you have to be careful about is to remember, if you're ever dealing with somebody else, they may not be using the same pressure units. Just a word of warning, if you remember back when we talked about the importance of units, this is what happened to the Mars orbiter. That was supposed to, it was a $125 million probe that was supposed to go in orbit around Mars. Well, two groups working together, one group, and it was a unit of force, but it was related to the pressure unit of force. So they were using two different pressure units, pascals versus, I'm trying to remember what the other one was, but there were two different units they were using there, and they didn't look at the conversion between units, and so it threw their orbit off considerably, enough to keep it from going into orbit and actually crashed into the surface of Mars. So just, it's okay to get comfortable with the pressure unit. Just remember, it is just one unit. We're not going to work a lot of examples here with conversion of pressure. I'm going to presume that you are comfortable enough with unit conversions now that if I gave you one pressure unit and you needed another, that you could do that conversion. But just as an example, if you want to go from atmospheres to millimeter of mercury, you just need the conversion factor for that. Atmospheres cancels out, leaves you with millimeters of mercury. So just pay attention to your pressure units. Make sure that you change them if you need to make the pressure match whatever you're looking for in the problem you're working. All right, so that's the first section of Chapter 11. In the next section, we'll start looking at individual relationships of aspects of gases. So pressure, volume, temperature, and number of moles. We want to look at how all of those relate one to another. Again, we'll do that in the next section.